Please welcome to the SuperCon stage, Sara Adkins.
Okay. Hi, everyone. Thank you. My name is Sara Adkins, and today I'm going to be talking about my project, Creating with the Machine, which is a set of compositions I wrote for human and machine musicians. So first off, algorithmic composition, what does that mean? By that, I basically just mean an algorithm that takes in some input and outputs some musical output. By interactive algorithmic composition, I mean that the input is a performance from a live musician, and the algorithm is able to output in real time. So the basic interaction model for this system is we want a closed loop between the human performer and the algorithm. So the idea is we have a musician that's improvising, they're kind of making up audio on the spot, and then we have an algorithm that's interpreting what they're playing and coming up with some sort of way to play music back to them. So they're kind of both playing off each other. It's common for human musicians to improvise with each other, so the idea here is to replace one of the humans with an algorithm. But the big question is, how do we get these two things to communicate effectively? Because clearly a musician and an algorithm are going to speak really different languages. And also, why do we even want to do this? I mean, what's the point of introducing algorithms into music? I mean, that's supposed to be a creative thing that humans are good at, and computers, we don't want to involve them. Obviously, humans are better musicians than computers, but computers are more accurate, they're faster, they're better at multitasking, they can keep track of more information. So maybe we can kind of combine the strengths of both these things and create compelling new music. We want to explore the idea of making randomness and automation useful to a musician's creative process and hopefully help them improvise in a way that they're not used to. But how do we do that? So I'm first going to talk about how we can get data from a musician's instrument into the algorithm. So I'll start with the simplest one, just a waveform. So if you mic a musician, as is common at almost every concert, you have an accurate sample stream of what they're playing. The issue with that is you can't really get many musical features just from looking at that audio wave. But if we take an FFT and we convert that audio wave into the frequency domain, suddenly we can see a lot more musical information. So in this spectrogram I have over on the right, you can see the x-axis is time, and the y-axis is frequency, so we can see what frequencies are prominent in the performance at each time slice. So from here we can do pitch detection, detecting what pitch the musician is playing, but more than that, we can determine more things about the tone of their sound. So different instruments will sound different even if they're playing the same note, and that's because there's something called timbre. Basically, they're playing the same bass frequency, but there are a lot of other harmonic frequencies that are playing above that that kind of create the voice of each individual instrument. So from a spectrogram, we can get that information. Another option for representing musical data is called MIDI. This is just a communication protocol. It represents exact notes, when a musician starts playing a note, when they stop, and how loud it is. You need special instruments to be able to use MIDI, but it is pretty common in musical performances. And now let's talk about if maybe we can get some weirder information from a musician's performance than just the audio they're playing. Musicians often use a lot of body movements when they're playing because they really get into their songs. Maybe we could get some information about their performance from that. We could also think about how can we get information from their breath. Are they holding their breath at certain moments? Are they breathing more intensely or faster at others? And also we want to consider gestures. Maybe we want to give the musician control of various parts of the algorithm, but we don't want to distract them too much from actually playing their instrument. So using things like accelerometers or IR sensors, we can get information like phrasing and subtle control that might not be so apparent from just the raw audio wave. Some technologies that I like to use for this are a Connect, which has really good limb tracking, or a Leap Motion, which is really good at tracking someone's fingers. All right, so we have some data from our musician. How do we use that to actually generate new music to play back to them? So the main point is that we don't want our musician to have to worry about how they're interacting with the algorithm. It should be intuitive for them. They should be worrying about making music, not worrying about, did I just play something that's going to break the algorithm? So that's the main concern here. We don't want them to get fed up with the technology. We want them to want to use it. So there are a couple of different options here. The simplest is just to use rule-based algorithms. You could say something like, when the musician does X, the algorithm should do Y. Or we want to map parameter A from the musician's performance to parameter B of the algorithm. Another option is to use Markov chains. Basically what that is it's a way to represent a bunch of different states and probabilities for transitioning between those states. So the example you see here is for a chord progression. Each chord is a state, and the arrows between them represent the probability of moving from one chord to each other. So for rule-based and Markov chains, I think something really important is that music theory is your friend here. Music theory is just the rules of how music works. They're made to be broken, but it's a good starting point for writing an algorithm. If you don't care about music theory and you don't want to learn that, luckily we have neural networks now, so you don't actually need to learn anything yourself. That's not true, but yeah, you can also, if you have a bunch of example MIDI inputs or example audio waves, you can train a neural network to output new music in a similar style. But for all of these, the most important thing is just to make sure you're using your ears. You can have a really good idea for an algorithm, but if you implement it and it doesn't sound good, then it's not really useful as an algorithmic composition. So as you're designing something, it's important to iterate by actually listening to make sure that you're coming up with something that's pleasing to you. Maybe other people won't like it, but it's only important that you like what you make. So, okay. Now I'm going to get into a little bit about some compositions that I've written. I'll go into the technical details of how I made them, and I'll also have a couple of audio recording examples. So the first piece I'm going to talk about is called Breathe. This is an example of a rule-based algorithm, and this is a composition that's for solo electric guitar. So there's this big flowchart here, and let's break it down a little bit. So we have our guitar input. The guitarist starts off this piece by improvising any key they want, doesn't matter. Their input then gets sent to a granular synthesizer. If you're not familiar with what that is, it's basically you take an audio wave and you chop it up into a bunch of tiny parts. Could be as small as like 10 milliseconds up to a second. And then you play them back slightly scrambled and overlapping to create an interesting effect. So that's one thing that's going on in the algorithm. The other is the guitarist is able to control an FFT using a foot pedal. So they play a note, they press their foot pedal, and we get an FFT snapshot of what they're playing. So now we can figure out what pitch did they just play. And more than just the bass frequency, we can also figure out what harmonics they were playing that made up that tone. Once we have that, we can then play each harmonic back as a sine wave drone, and this kind of creates like a background for the piece. And the guitarist is able to layer a couple of these, and the oldest gets deleted as it makes a new one. So that's the guitar input. And then we also have a microphone that's taped to the performer under their nose, and we're using this to capture their breath signal. So basically, as they breathe out or they breathe in, the microphone will get hot and the amplitude will increase. As they're holding their breath, it'll decrease. So we kind of have this amplitude envelope of their breath that we're creating. And this is what we're using to map to parameter changes in the algorithm. So as the amplitude of the breath signal increases, it first affects the granular synthesis. the grains get faster and more overlapping. So it starts to sound a little bit more scattered and chaotic. And then we're also going to start changing the volumes of the different drones. So as I said before, what makes up the tone quality of an instrument is the ratio in which you play the harmonics. So if you vary the amplitude of those, you start to create different tones. So as the amplitude of the person's breath increases, these drones start to move around faster. Cool, that's the technical part. I also have a couple short audio recordings of parts of the piece. This is a picture of me performing it on the right with a guitar, and then on the left, that's my professor wearing a wizard robe. So in this first excerpt, I think the best thing to pay attention to is listening to the drones. There we go. And then in the second part, you're going to hear more of the granular synthesis in the piece. All right, so next piece. This next piece is called Recurrent Neural Networks on Bach. And as you might guess from the title, this is using neural networks in the algorithm. So like 350 years ago, there's this dude, his name was Bach, and he wrote a lot of music. A lot of it was good. Yeah. All right, so basically what I did here is I trained a three-layer LSTM on 405 Bach chorales. So what is an LSTM? So it's basically a neural network where the output is fed back to the input, so it's able to remember information from previous states long term. This is especially useful in music because, as you can imagine, what a musician plays next is very dependent on what happened previously. So if we're going to try to learn how to do that with a neural network, we want to make sure that we're feeding back the output and that we're being recurrent. And the output of the neural network is a 4-voice chorale in the style of Bach. A chorale is kind of like a church hymn. It's a short sung piece with a soprano, an alto, a tenor, and a bass. It's usually rhythmically pretty simple, but the harmonies are complex. And a lot of the music that Bach wrote is kind of the basis of tonal harmony and music theory. So I trained up this network using TensorFlow. It took about 3 days, but the interesting thing here that I did was I would save a snapshot of all the model weights every half hour during training. So basically, I had this whole folder of how the algorithm was performing as it learned. So the first snapshot, it knows nothing and it just outputs random notes. If you look at a checkpoint like a day into training, it's kind of starting to get the idea. And if you look at a checkpoint at the end of training, it's actually generating some pretty cool harmonies. So that's how I generated kind of the content for this piece, but the performance is kind of another loop. So basically, Mike. Basically, the performer has access to a MIDI controller that's able to determine how fast the algorithm is going to move through the checkpoints. So we always start by playing music that's generated randomly before the network has learned anything, and we keep moving until we get to a point where the algorithm has learned to generate tonal harmony. So what's interesting here is the performer actually doesn't have any control over the exact notes that are played. They're able to control what checkpoint we generate notes from, but they're not able to control what those notes are. They can pause on a note if they like it, or they can speed past a section if they want to get past it, but that's about as much control as they get. So the TensorFlow model will output a phrase, the performer will hear it back and can choose how fast to move through it. They also have some other controls for shaping effects of the piece. And I'll play a couple examples from this at various stages of the model. So the first, this is when the neural network has just started training, so it's basically outputting random notes at this point. Or maybe the audio won't work. Oh, there we go. Yeah, so it sounds kind of creepy and eerie, but it's just random notes. The network knows nothing at this point. Now let's look at a section from the middle of training. Hopefully it's starting to get a better idea of harmony at this point. So at this point, we're starting to hear that it's playing actual chords that don't sound awful, but there isn't really much flow between the chords. It doesn't really feel like it played an actual phrase. So finally, let's listen to an example from the end of the piece where the network has been fully trained. So that's more what we want. Like, there was a cadence, it resolved. It might not be as good as Bach, but it's getting there. Cool. So the last piece I'm going to talk about is called Machine Cycle. So this is an ensemble piece, but it kind of has a soloist in it that is playing a MIDI keyboard. The reason for this is I didn't want to deal with having to do pitch detection. MIDI is an easy way around that. So how this piece works is the MIDI keyboard player will be playing phrases and improvising. And as they play, the algorithm is going to randomly grab phrases from them. And then from that phrase, they're going to create a Markov chain. So it's going to add some potential embellishments to their phrase. That'll be maybe notes that could be between jumps, maybe some rhythmic alterations. When the phrase starts, does it start in an upbeat or a downbeat? Maybe adding in more notes. And then it'll save that in a bank. And as the musician continues to play, more chains will be added to the bank and we'll delete the oldest. So we're always keeping track of phrases that the musician has played most recently. And then during the piece, the algorithm will output phrases that are generated from a Markov chain. So the musician will be hearing back phrases similar to what they played, but with some embellishments. So there's kind of the closed loop there. They're playing off what the algorithm has played back to them. Also in this piece, there is a conductor who is leading the other ensemble members and controlling some different parameters of the algorithm, like how often phrases are altered, how often do we skip notes, how often do we play it half or double tempo, basically controlling how different the phrase that's played back is from the original phrase. And on the left here, you'll see a picture of the score that I wrote for this piece. Unlike a traditional score, it's not dictating like exact notes that all of the performers have to play. Basically, the top line is for the keyboardist, and it's kind of telling them when to improvise, when to pause, when they should build, dynamics. The control is for the conductor. what they should change about the algorithm. There's also a guitarist that's kind of acting as a counter melody, and the drones that are just filling out the background. So it's just to give the musicians a structural outline of the piece, and they're free to improvise the specific notes. And the conductor is responsible for leading the musicians through the piece and controlling the parameters. And so now we can listen to an excerpt from Machine Cycle. All right, so those are the pieces, and I obviously did not write all this from scratch, so I just wanted to take a minute to talk about the tech that I used to build these. So for recurrent neural networks on Bach, I use TensorFlow, which is a popular machine learning framework for building deep neural networks. Google in particular has a cool open source project called Magenta that is dedicated to creating art and music using machine learning, so I use their tool chain a lot. Most of the code I wrote was programmed in Python, and they have a lot of useful packages for music, the MIDI library, Mido, and if you're going to be working with MIDI and generating MIDI, you definitely want to be using a scheduling library, so you're not continuously writing sleep statements in your code. So Sched is the library that I use for that. Something that I also use a lot is graphical programming languages. So it's basically, if you've never worked with one before, functions are kind of like blocks, and you draw wires to connect them, and that represents like a signal flow chain. So when you're working with an audio algorithm, it's a really nice way to represent that. I use something called MaxMSP, which is a paid software. It's a couple $100, but there's also an open source version of it called Pure Data that's really nice. And both of those have a lot of externals that people have written for them. Sigmund and Fiddle in particular, I used for pitch detection in Breathe. And then the last thing I'll mention is message passing. So if you're working with a lot of different pieces of hardware or a lot of different applications, Open Sound Control is something I use a lot. It's a UDP messaging protocol. It's just really useful for speedily passing information around. And my name is Sara Adkins. I have more of my music on my website, as well as full audio recordings of all the pieces I talked about. I have my code on my GitHub. It's kind of well documented, some of it. And there's my email. Feel free to email me with any questions, or just come and talk to me later in the conference. Thank you.